Okay, then let's continue with statistical methods. So the topic today is GLM theory. So last time we saw an introduction to the GLM analysis of fMRI data from the mass univariate viewpoint, and talked about the intuition, how the specificity of a brain region, which is then imaged in a voxel, is mapped onto beta parameters, so that these beta parameters somehow reflect the effect that specific conditions have on brain regions. And after the Christmas break, I would like to go more into how the design matrices are generated and what kind of issues arise in this context, and how you do single and multiple subject analysis. So things that are fairly specific to fMRI. But I think what you also need, and of course this is also how I taught this course in the past, is that you at least have some idea of why one can do these statistical tests on the beta parameter estimates. So you know that when you look at the output of a fMRI analysis, you look at what is called statistical parametric maps. So these are maps of T statistics, or of F statistics, usually of T statistics. And you all know from undergrad statistics that you can use T values to do statistical tests. So to check whether a T value is larger than some critical value, and then decide whether you reject the null hypothesis or you don't reject the null hypothesis. And these things we didn't talk about last time, and we will not talk about much in January, because they really refer to the statistical theory that comes with the GLM. Now, in the past, I basically discussed the GLM theory over the whole winter term. So there are these lectures from last year where I think it's 30 lectures on GLM theory. That's nice, and everything can be worked through and be traced and so on. But of course it also takes a lot of time, and it doesn't concern fMRI analysis per se. So this year I decided to try to fit these 30 hours into the 2 hours that we have today. Of course this will be more kind of a sketch of the whole thing. So not a Loriot sketch, but a sketch in the sense that, anyway. So it will be a sketch, and it's primarily, I will try to sketch the theory, highlight certain things, and basically give you the keywords where you then are encouraged to clarify things for yourself more. So I try to explain things, but we basically have these 2 hours, and there will be things that you should clarify for yourself. So the PMFN material, as it is currently online, covers a lot of this. I think the only thing that it doesn't cover right now might be actually the T statistics, because I still have to polish that, but I just finished polishing also the estimation of the GLM and the distributions. So there is a lot of material. Then you have the videos, and then finally also this will not be, I'm not quite sure how to handle it with the exam, but definitely you will not get the normal questions that everybody else got like for these 30 hours, but maybe none, or maybe one or so regarding the stuff that we do today. So don't worry, but it's actually very important. But the thing is, this year it's like this. Next year it might be different. It's always how I think things are good at a specific point in time. So that's the GLM distribution theory, and it essentially comes down to roughly something like 6 or 8 or so equations that I will try to elucidate in the following. So the first thing that we need to talk about is this. And the second thing that we need to talk about are those two here. And they can, oops, no, almost, they can actually be related to what we discussed last time as model formulation. So that's the first equation, that's model formulation. This is parameter or model estimation. And once we briefly talked about those, we have to talk about the parameter distributions, which are given by these equations. So essentially, if you know what these things that I'm currently writing down mean, then you're basically set, because then you have a good idea about the GLM distribution theory. This one, and then finally the T statistic, which takes this form. So where actually the probability density is given by the T distribution, as you all know. So this latter part here, so these two things are actually model evaluation. And that's essentially what I've just written down. This is the whole distribution theory of the GLM, and not much more. So if you know, or at least have an intuition about what these things mean, then you're actually quite far into understanding GLM theory as a probabilistic model theory. And yeah, I want to go over these 4 things then now. And we start with model formulation. Which comes down to this. Let's make this smaller. To this statement here. So now what this describes here is a probability density function, or what it means. It's a probability density function. And this is already one of the terms I'm highlighting here. So if you're not quite certain what a probability density function is, as opposed to a probability, have a look at that. You all know a probability density function, namely the univariate Gaussian. It looks something like this, where you learned that there is some expectation and there is some standard deviation or variance parameter. And these Gaussian distributions, they are commonly specified in terms of probability density functions, which are functions. And so the Gaussian probability density function is something that looks like this. So I guess you've seen this, or I hope that this is this function. So what I just plotted there, and it's just a function like any function. I hope I didn't forget anything. So that's just this univariate probability density function, and this is abbreviated here by n, so for normal or Gaussian, and it's the probability density function over x, and has as parameters an expectation parameter and variance parameter. Yeah, so I assume that who has seen the Gaussian before? So everybody has seen the Gaussian, so you know that. Good. So that's not a surprise here. Good. So then a fundamental thing that you can already now associate with the GLM is that there's somehow a Gaussian assumption in there. What I've written down here is actually a multivariate Gaussian distribution. What is written down here is a probability density function over some data y r n. So n, remember, that's the number of data points. And remember again the intuition that we discussed last time, that in the application to fMRI, the y is the, what is the y? Does anyone remember that? What do we model by y if we apply the GLM to fMRI data?
The single data points.
The what?
The single data points.
And what are the single data points?
It's a signal in time.
Mm-hmm. And where does this signal originate?
Electromagnetic field.
Yeah, but more specifically, where in the brain? So is this from how many voxels? From one voxel, yeah. So this is because when you acquire the data, of course, you measure many voxels, but what we are doing here with this mass univariate viewpoint is that we consider the data of a single voxel, one voxel, over time. And these time points, and there are n in total, these are the images that we acquire. Yeah? So always be clear about that, because that's actually the simplest thing about the whole thing, what the data is. So that's the data, that's our EPI time series or MR signal time series from a single voxel. And what this probability density function here specifies is a probability density over the entire time series. So for each individual data point in this time series, which has n entries, and this probability density is given as follows. So I'm first writing down now briefly the multivariate Gaussian, and then I explain why it has this form. So the multivariate Gaussian is a probability density function like the one that you know, but for vectors. So instead of x, sorry, that of course doesn't make any sense here. Instead of x being scalar here, we are now looking at x's that are n-dimensional, or y's that are n-dimensional. And this is, again, just a function which is fairly similar to there's something a little bit wrong. This is very multivariate, sorry. This is what I want. To the univariate one. So it has this 2 pi factor in there, it has the square root, it has an additional n in there, it has the inverse of a variance parameter in there. So here you have the variance parameter, here you have what is called a covariance matrix, and it has the exponential term in there. So it has the deviation between x and the expectation parameter scaled by the inverse of the variance, and has the square of that. So if you are a little bit okayish with vectors and matrices, it's relatively straightforward to see that these two things are fairly similar in terms of what they do. There's a whole chapter in PMFN only on these multivariate Gaussian distributions, so have a look at that. The thing is, how you should imagine that is as follows. So if you have like here you have a univariate thing. If you have a two-dimensional thing, then two-dimensional Gaussian has also this bell-shaped, but in two dimensions, something like this. So it's like a real bell. If you go to 3 dimensions, it's even harder to imagine actually. So you have to kind of imagine swimming through something, and then it gets brighter, and then it gets less bright again. And in higher dimension, one cannot really imagine that anymore, so it doesn't matter anyway. The most important thing here is that we assume this specific form of covariance matrix. And this covariance matrix is just a parameter of this. And this assumption here, and this is now the important bit, this assumption that the covariance matrix is what is called spherical. This corresponds to the idea that all the data points, so these ni, are independent, so they are each specified according to an expectation parameter, which is given by the specific row of the product of the design matrix and the beta parameter vector and a variance. So what does that mean? So remember again, last time we looked at one design matrix. So we have this design matrix that we looked at, looked something like this. And then we multiplied this by a beta vector, which had 2 entries, something like, for example, this. And from this, we got a prediction for our time series. Yeah? So remember that we, based on the product of the design matrix and some parameters that we set, we got a prediction. So we did this onset vector convolution, predicted time series business. So I hope you remember that. And then we got something like this, which would be a predicted time series. Now, this way with specifying over the data multivariate Gaussian with its expectation parameter given by x beta and this covariance matrix given by sigma squared times in. What that means, as also then written here, is that it specifies a univariate Gaussian, so something that you know, a univariate Gaussian over each individual time point with expectation given by the specific entry in this vector that is given by the product of x beta and the same variance parameter. Yeah. So if what I plot here now, so this red thing, if this is our x beta, remember x beta is a vector, you can also call that mu, and it has entries mu I, which of course, now I connected all of them, you can also view as these dots here. So this is essentially this. What the multivariate Gaussian with the spherical covariance specifies is that in addition to this expectation, the model predicts Gaussians over these expectations. And one way to visualize this is like this. It's helpful, it's horribly wrong, but it's helpful. Yeah, so for each data point there's a Gaussian, and I'm trying to draw Gaussians here. That is specified over the expectation. Do we have all of them now? Almost. These are all Gaussians. So tilted ones. So this is supposed to look like this. Yeah. Only that it's shifted by 90 degrees. So these are our these are the Gaussians, and that what one can show is analytically is that if you assume a product of n univariate Gaussians that all refer to different data points and have different expectations and the same variance, that this product of probability density functions can also be written as a multivariate Gaussian probability density function that looks like this. Yeah? So essentially writing the data as, or given the probability density function, this multivariate Gaussian here, with importantly this spherical covariance matrix to the data, implies that each data point has its individual error distribution, all with the same variance, but with different expectation parameters, which are given by the product of x beta. Yeah, that was quick. There is a slow version, which is in like 4 or 6 lectures on YouTube.
I have 2 questions. Yeah. Why is it horribly wrong to speak?
Yeah, it's horrible.
Why?
Yeah, because what I'm doing here, so this is MR signal space, and now I'm drawing some probability density functions somewhere in this. It doesn't make sense. It's just a visualization. Yeah, but don't start thinking about it. So these, all of these Gaussians, they are univariate things that exist over yi, yeah, and have meaning if you plot them like this, but they don't exist in this 2D plot. It's just a visualization that is you shouldn't think about.
Okay.
Yeah?
And when they estimate the parameters,
we are not there yet.
But just one quick question about so you would normally do log transformation, right? In practical.
Yeah, but we are not there yet.
But do they really use this multi?
Yeah.
Gaussian?
Yeah.
Okay.
But
so
we are not there yet. We will be there in like 15 minutes.
Okay.
Yeah, but they do. Other questions? So this is what this formalization of the model means. So the data that we're trying to model is the time series of a single voxel. We model it like we saw last time with the product of a design matrix and a beta parameter vector. And in addition to that, we assume that this is the expectation of a multivariate Gaussian, which means that of a multivariate Gaussian that models independent univariate Gaussians, and this is embedded in this covariance matrix. Yeah. I think I want to leave it at this because we have to go on. So the keywords here to get into this a little bit are probability density functions, multivariate Gaussians, of course, and this is actually so that the equivalence between the spherical covariance and this product and this independence, this is also spelled out in PNFM. This is just follows just if you look at the functions, so at this function and at this function in detail, then you see that this is actually the same thing. What it means is, maybe one last thing in terms about the intuition of this model, it means that what you would expect without having any data, what you would expect is, depending on your design matrix and your beta parameters, we saw last time, of course, that you can get these predicted time series. And now, in addition, it is assumed that these are just the expectations of Gaussian distributions. So if you now sample this, you would assume that whenever you have this expectation there, and of course these expectations are discrete, so this is why it's not always helpful to just draw a line. So these are our expected values. If you now sample this, that you always have an independent error contribution that depends on the variance. So for example, you sampled something here, you sampled something here, you sampled something here, 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 and that then observed time series would look like this. I'm just doing the whole thing. Sometimes you sample actually where it's supposed to be, but this is all happening without any data. This is just what the model says, yeah? But the model says that it's likely that you observe time series that have bumps where the expectation has a bump, so where your onset vectors with the hemodynamic response had a bump, and elsewhere and also around these bumps you have Gaussian noise. This is essentially what it means.
So just maybe to recap understanding. So the expectation value of every univariate Gaussian over a data point is an estimated data point, and then
No. Nothing has been estimated so far. There is no. This is just model formulation. This is without any data. This is just a mathematical model that I've now written down.
But what are those points now over which these univariate Gaussians are computed?
These points are x beta I.
And what is x beta I?
That's the ith entry in the expectation vector. So the when I plot this with the line, that's a little bit incorrect. So the model only has this black dots. Yeah. So the model has just, that there are columns of the design matrix which get multiplied by the beta vectors, by the beta vector, and this just results in one vector of n points, and these points are these black points. The thing that I draw in black in between does not exist in the model, and it also doesn't exist in the data. It's just a vector that is plotted, and I've just connected the dots to make it look nicer. Yeah? But there is no data anywhere here, because this is a mathematical model that you can implement in a computer and simulate, but data has not been observed in this setting. Yeah? But now, are there more questions? No? But now we observe data. And then we get to model estimation. And model estimation for the GLM works in an analytical setting. So first of all, you don't need to estimate these parameters numerically by shifting something around, but you can maximize or minimize certain function in terms of the deviation between your observed data and the model analytically. And there are, so one can, and this is how I do that in the first instance, talk about maximum likelihood estimation. So the beta parameters of the GLM are estimated using maximum likelihood, or ordinary least squares, which is the same thing for a Gaussian likelihood function. So what happens there? Has anyone in undergrad statistics come across ordinary least squares? Least squares? Maybe? Yes? Least squares? Yeah, that's, I guess, was ordinary least squares. Maximum likelihood? What do you remember about maximum likelihood? It's not complicated.
No, but we didn't do it outside. Well, I remember it was I basically remember that it's the opposite, kind of the opposite of what we did with hypothesis testing before, but it was not having that data saying something about the hypothesis based on the data you have, but the other way around.
I think I know where you're getting at, but it sounds very weird. The idea of maximum likelihood is essentially to take those parameters as parameter estimates that maximize the likelihood of the data, and the likelihood of the data is just the probability of the data under the model. So likelihood doesn't mean anything else than probability, and the way that maximum likelihood works is that one defines a likelihood function, and the likelihood function is a function of the model parameters, and in our case the model parameters are our p-dimensional beta value and our variance parameter. So we basically that one is a function of that, and maps this onto usually, if you're dealing with parametric models that are defined in terms of densities, into a probability density. So for the GLM, what this means, you take the beta parameter, you take the variance parameter, and let return this function the likelihood of these parameters. That's how one can speak about it, the likelihood of these parameters for a given data point. So the important thing is how this is defined. And this is defined exactly as the model, as the model we are talking about. So in this sense, I think it's not complicated, because this is just the probability density of the data, and now we are just doing something, we are basically switching perspective, and maybe this is what you meant with it's kind of the opposite. So we're switching the perspective. So above we have we looked at this Gaussian, this multivariate Gaussian, as a function of the data, and for fixed parameters beta and sigma square. And now we're switching the perspective. We assume, let's do that here, that y has been observed. So we assume that there's a vector y that has been observed. So this is now the data. This is our time series from a single voxel. That's data. And now we're trying to find settings for this parameter beta and for this parameter sigma square that maximize, and hence maximum likelihood, maximize this likelihood function. Yeah. So we try to actually find the arguments that maximize the likelihood function here. And these arguments we call maximum likelihood estimates. So beta ML, maybe we do it a little bit more exact. So beta ML is the argument that maximizes the likelihood function with respect to beta. And the maximum likelihood variance parameter is the argument that maximizes the likelihood function with respect to sigma square. Yeah. So essentially you should think about this as this is a function, and it's just the multivariate Gaussian probability density function. You have the y in there, and now you're varying the beta and the sigma square, and you try to get two values of beta and sigma square that maximize the output of this function, which is just a single number. And once you found values of the parameters beta and sigma square that maximize this function, you call these maximum likelihood estimates. Yeah? That's basically the idea of maximum likelihood estimation here in the specific context of the GLM. So again, the key term here is maximum likelihood estimation or maximum likelihood. Have a look into PMFN, what a likelihood function is and what a log likelihood function is, so that you get a little bit of an idea how that works in general. Here, of course, it's the application to the GLM. And now a specific thing. So that's just maximum likelihood estimation. Oops, where's my? Hello, am I recording? Am I not recording? What's going on? Am I still not recording? Anyway, it is. I'm not recording. Interesting. That's not good, but you have the last year's lectures anyway. The thing for the GLM is that one does these things analytically. This means that one uses the way to maximize functions analytically like you did in school. So does anyone remember how you maximize functions in school, how you find the maximum of a function?
Derivative.
Yeah, and then?
And then like C0, I think.
Yeah.
The x point 0.
Yeah, so basically the way you maximize or find extremal points in school and analytically in general is that you compute the derivative with respect to the argument that you want to maximize the function to, and then solve the necessary condition for a maximum, which is the condition that the derivative equals 0. And this one can do analytically for the likelihood function. So that is just this function here. And it's a little bit easier if one transfers, or if one takes the log of this function. The log transform doesn't do anything bad to the likelihood function, so it keeps the same points for the maximum. So the log is a monotone function, so monotonically increasing. So if you have a maximum without the log, you also have a maximum with the log, so it doesn't change anything, but you can then easier analytically compute the maximum. So essentially what you need to do is compute the derivative of the log likelihood function, for example, with respect to beta, and then set this derivative to 0. The thing is, beta is in general a vector, not a single scalar, so you have to compute what is known as the gradient of the likelihood function, which is the concatenation of all the partial derivatives with respect to the individual parameter values. And if you do that, what happens is that you are led to a system of equations, namely the following. Which are known as the normal equations. And the normal equations are equivalent to the idea that the gradient of the likelihood function with respect to beta vanishes. So without going into how to compute the derivative of the likelihood function, what I'm telling you is if you compute the derivative of the likelihood function with respect to beta and set it to 0, you get to a system of equations that takes this form. So essentially saying the derivative of the likelihood function with respect to equals 0, which is actually a p-dimensional 0 vector, is the same as saying the transpose of the design matrix times the design matrix times the beta parameter vector equals the transpose of the design matrix times the data. This is the normal equation. These are what's called the normal equations. And this is essentially just the necessary condition for a maximum or minimum, so an extreme point. And this can then just be solved for the value that the maximum likelihood estimate takes on. So basically you try to isolate the beta here. So you multiply both sides with the inverse of xtx. And then you have here the inverse of a matrix times a matrix, so that goes away, and you are left with this formula for the maximum likelihood estimator. And then usually these estimators get ahead because it looks nicer, and sometimes if you want to emphasize that this is derived by maximum likelihood, you can put a little ml to it. Actually, the ordinary least squares estimator has exactly the same form, because that's for the beta estimator. It's equivalent whether you do maximum likelihood estimation or ordinary least square estimation. So what this means is that you have a little formula here that you can use on your data. Yeah. So here, this is data, and you just have a little thing, namely the product of these design matrices, the inverse of the design matrix, that you multiply the data by, and then get your parameter estimates. Yeah? Essentially what is happening is that you correlate the design matrix here, so you have the transpose of the design matrix, you correlate this with your data, so you compute the multiples of each entry of the design matrix with the data, and then you sum it all up, and if these multiples often go together, you get something large, and you normalize that by, in a way, the variance of the design matrix. This is how the beta parameters are estimated. But this estimator, yeah, you will see everywhere, so that's the beta maximum likelihood estimator in the GLM. And it's not numerical, but it's analytic, so that's the big difference to when you do maximum likelihood estimation, where you always shift around the thing. So that's how the beta parameters get estimated. If you do the same thing, maximizing the likelihood for the variance parameter, you actually end up with the following. So one can plug in the beta estimate into the likelihood function, and then gets as estimate for the maximum likelihood estimator the following. This is the deviation between the data and the prediction based on the beta estimate, and you do a sum of squares here. So this thing here in the numerator is just yi minus x beta hat, so the prediction based on your estimate I squared. Yeah, so this is a sum of squares. So the residual sum of squares, that's I guess something that you know. So the residual sum of squares, that's this thing. And if you do maximum likelihood, it's actually divided by n. And then it turns out that this is not a very good estimator because it has a bias. Hence, the maximum likelihood estimator for the variance parameter in the GLM is never used, but the corrected maximum likelihood estimator is used, which also subtracts P. And this corrected maximum likelihood estimator is actually called a restricted maximum likelihood estimator. And when one uses the restricted maximum likelihood function, then this is the estimator that one finds. So essentially, this the beta parameter is estimated basically by applying this little formula to the data. The variance parameter is then estimated by computing the residual sum of squares, so the remaining difference between the prediction based on the beta estimate and dividing this by n minus p, which is the restricted maximum likelihood estimator.
What's RSS? Excuse me.
That's the residual sum of squares. This is just the the sum of the squared deviations between the prediction based on the beta maximum likelihood estimator or the beta estimator and the data. Yeah. Of course, one can also do this a lot slower, and you will find on YouTube these lectures that go about this a lot slower. But this is essentially, these are these two steps, model formulation and model estimation in a nutshell. So in a way, you have to decide for yourself what is unclear to you now, because I'm not quite sure what exactly is unclear. Of course, a lot of things can be unclear, and I see that. But yeah, so if you have questions, I can try to answer them now. Otherwise, the key points for the estimation are definitely principle of maximum likelihood, likelihood function, maximizing a function analytically, and then applying this in the GLM, which yield the normal equations. Once you're happy how you get from the derivative of the likelihood function with respect to the beta parameters to the normal equations, then it's just a question of matrix inversion. Then you get the beta estimator. Doing the derivative of the likelihood function with respect to sigma square is a lot easier in a sense, because it's just a single number and it's just a derivative, like you are familiar with derivatives from school.
I don't see any derivatives there, so I don't know, maybe...
No, these are the solutions. So the derivatives, here is one derivative. So this is the...
what is it? It's a J or it's a delta?
This here, that's a nabla. A nabla.
Nabla?
That's the gradient operator. Because the derivative for a function of vectors, this is of course also something that is just skipped over here. So the derivative of a function that has as inputs vectors is the gradient of this function. So the derivative, I shouldn't be more specific, the derivative of multivariate real-valued functions. That derivative is called a gradient, and that's the concatenation of all the partial derivatives. Which are just normal derivatives. The good thing is if you go from, if you're happy with that and get from the gradient being 0 to the normal equations, yeah, then you basically have an equivalent condition to the condition that the gradient is 0. And here, yeah, I didn't do the derivative, so what you need to compute to do this is, of course, you need to compute the derivative of the likelihood function with respect to sigma square at the location beta, and once you have the derivative, set it to 0 and solve, and then you get the sigma hat square divided by n and find that it's not good, and then you have to do the minus p. So this is, of course, I mean, there's to go about this in detail, of course, it takes a couple of hours, which I'm not doing right now. So if you want to see the calculations that happen there, they are, I think, in the YouTube videos, and they are, of course, also in the script. And yeah, but this is where the derivatives are. No? Other questions? So now, basically, what we can do is we can compute better. We can, if we have some data, we can compute an estimate of our effects and an estimate of our errors, of our error variance. Yeah. So remember last week when we looked at the true but unknown beta values, or the beta values that I just set. I also computed the estimates, which are then roughly, if you do this simulation, they are roughly the same as the values that are used for the simulation. In real life, of course, you don't know some simulated parameter values. You just know your data. You can apply your design matrix to this data here. and then get some better estimates. And basically by looking at the residual sum of squares, you get an estimate of the error variance. And of course in fMRI, you will now do this for each voxel. Yeah? So for each voxel, you compute an estimate of the beta parameters and an estimate of the variance parameter. And then, based on this, you can do inference or statistical testing. And I would suggest we have a break now, and then at 11, I tell you how you can do statistical testing based on this. Good, let's have a break.